Hello friends, this video on Chemical Kinetics Part 6 is brought to you by examfear.com. No more fear from exam. The most important factors that impact the rate of reaction is the concentration. On the left hand side, if you see the more concentration, right hand side less concentration, right? The target is still same. Now, one car is being assigned to break this tower. In this case, instead of one car, we have almost 9 cars. Obviously this will be fast, right? 9 cars can break this tower more easily than one car. So here we have more concentration on the left and less concentration on the right. Thinking from the car and the tower example, right? The more the cars we have, more easily they can break the towers. The more faster the reaction will be. Left hand side we have less concentration of the cars. It will take more time to break the tower. So the reaction will be slow. And here it will be fast reaction. We'll take some examples of this. And if you increase the concentration, that means more molecules, that means more collision. More collision, that means more probability of getting product. Less concentration on the left hand side, that means less collision, less number of collisions. Less number of collisions means less probability of getting product. So the rate is slow here. And it is fast. A good example is let's suppose we take this zinc in both the beaker, same amount of zinc in the same form, and we'll take 1 MSCl in this flask, and in this flask we'll take 20 MSCl. You see, this is higher concentration, this is low concentration, right? This is my low concentration, this is high concentration. Now I'll put this 1 MSCl and 10 MSCl in this beaker and let's see what happens. If you see 1 MSCl you put in this beaker, reaction starts. You put 20 MSCl in this beaker, the reaction starts. But if you see, the rate of reaction is different. You can try this in the lab. You see, the rate of reaction is less. The hydrogen gas coming out is less. In this case, more and more hydrogen gas is coming out. So on the left hand side we had low concentration of HCl and few hydrogen gas came out. On the right hand side we had high concentration of HCl, right? Zinc is same in both cases. More and more hydrogen gas came out. So if you see, that means the reaction rate is more on the right hand side, the reaction rate is less here, right? More rate of reaction, less rate of reaction. Less concentration, high concentration. One more good example can be a candle. If you see the candle, what happens is the carbon actually burns in the presence of oxygen to give carbon dioxide. Correct? Now oxygen comes from air. So if you somehow close this with a beaker, you take this beaker and you cover this. Once you cover this, the oxygen is limited. After some time, the oxygen will get exhausted, right? The concentration of oxygen will go down, right? The concentration of oxygen will go down. If you see, it will start diminishing. And finally, it will go off. Let me repeat this equation. This is the candle. It is getting sufficient air from the surrounding. It is working fine. You cover this with this beaker. The oxygen will get consumed. After some time, the candle light, if you see, it will get diminished and then it will go off. See, that means the rate of reaction is depending on here the concentration of oxygen. Earlier, the concentration of oxygen was more. It was perfectly fine. Now the concentration of oxygen is getting diminished, so the lighting is also less and finally it goes off. Correct? So the rate of reaction has a huge impact on concentration of the reactants. Since for a given reaction, for example, A plus B gives C plus D, the concentration had a huge role. So chemists thought, okay, let's focus on the concentration first, right? On the impact for the rate of reaction, right? So we'll be talking about how concentration is impacting reaction rate. That is what we'll be focusing on in this slides. Now, this chemist, they found that the chemical reaction at a given temperature may depend on concentration of one or more reactant. That means it may depend on the concentration of A or concentration of B or C or D. Correct. So the representation of the rate of reaction in terms of concentration of reactant is called rate law. So they came up with something called rate law, and rate law is nothing but my representation of rate of reaction in terms of concentration of reactant, and that is called rate law. Correct. It's also called rate law, or it's also called rate equation. It's also called rate expression. Three different names: rate law, rate expression, rate law, rate expression, rate equation. Right? And we have seen in the past example that the rate of the reaction decrease with the passage of time. Right? The moment the concentration is decreasing, the rate of reaction decrease. We have solved one numerical also. Right? So we can say that my rate of reaction is directly proportional to concentration of reactant. And this is what we have seen in one of the examples in the past few slides. Correct? That is something experimentally it has been seen. Now let's suppose there is a reaction A plus small b gives small c, or let's put the value here: small a, small b, small c, and small d. That means I am putting some stoichiometric coefficient here. That means small a moles of capital A plus small b moles of capital B gives small c moles of capital C plus small d moles of capital D. Now experimentally it is seen that, based on experiments, please note this is all experimental. Experimentally it is seen that the rate is proportional to reactants A and B, but instead of to the power A or B, it is to the power X or Y. This X and Y are experimental value. They may be equal to A and B, may not be equal to A and B, right? X and Y are not equal to A and B always. Sometimes they are, and they are experimental value. And rate, till now what we have seen, rate is nothing but my change D minus of change of reactant with time, or you can say in this case minus 1 by A change of A by change of T, or minus 1 by B change of B by change of T, or plus 1 by C change of C by change of T, plus or plus 1 by small d change of capital D by change of T. This is what we have seen. This is all rate, right? This is the same rate, actually the same rate we are trying to write in terms of concentration. So experimentally seen that the rate, we have seen that one question, the rate of the reaction decrease because the concentration of the reactant decreased. So we concluded that the rate of reaction is dependent on concentration of reactant. Please note, it's a concentration of reactant only reactants, not the product. Correct. So rate law is nothing but we represent the rate of reaction in terms of concentration of reactants. And experimentally it is seen that rate is directly proportional to concentration of A and B, that is my reactant, but the power is not the stoichiometric coefficient, it is some values X and Y, and that is experimentally formed. So this form of equation is called differential rate equation. So in this case it is a proportional. I want to give a constant value, so I can say that rate is K of e to the power X b to the power Y. Correct. So this K is called rate constant, and this whole equation is called rate equation. Instead of rate I can write minus dr by dt also, because this is nothing but change of reactant with a minus sign. Why? Because the reactant is going down, nothing but K of e to the power X B to the power Y. This is called differential rate law or differential rate equation. Correct? This K is my what? K is my rate constant. If you see, concentration is changing, the reaction rate is changing. And please note, these are all experimental value. Let me repeat again, these are all experimental value. This X and Y are experimental value. Correct? So you want to define the rate law. Rate law is nothing but the expression. It is the expression in which the reaction rate is given in terms of molar concentration of the reactant, with each term raised to some power, which may or may not be the stoichiometric coefficient. I told X and Y may or may not be A and B. Generally it is not, right, of the balance reaction. So that is my rate law. Rate law is nothing but the expression in which the reaction rate is given in terms of molar concentration of reactants. Correct? So how do you find rate law? How do you find the rate law? For example, let's take one example. I have this NO. This is react with O2 to give NO2. This is my balanced reaction. Correct. So in this case, my rate will be K times concentration of NO to the power X, concentration of Y, O2 to the power Y. And XY has to be experimental. Correct? Because I told X and Y has to be found experimental. So let's do experiment. So let's do experiment 1 here. Let's suppose experiment 1, and let's suppose this is my amount of NO. We'll put here. This is amount of oxygen. We'll put here. And this is rate of formation of NO2. We'll put here. Right? This is my experiment. In case of experiment 1, let's take some X concentration of NO and some X concentration of NO2. And let's suppose the formation of NO2 came out to be 0.02 moles per liter per second. Just assuming some values. In experiment 2, what we can do is we can double the concentration of NO and keep the concentration of O2 be same, and then let's suppose it becomes 0.08 mole per liter. This is all experimental, right? This is rate of formation of NO2, experimental value, experimental data. Like all these are experimental data only. These two we are changing and this we are calculating. So if you see, from X to 2X we made, and this becomes 2 to 8. Correct? What does it mean? Sorry, it becomes 4 times, 2 to 8. 2 became 8, that is 4 times. Correct? So X became 2X, it became, but if you see it's 2 times only, but if you say X square here, let's suppose, it's become 2X square, then I can say X square is 4X square, right? 2 times, 4 times actually here. See, there is X here, there is X here, so instead of X, let's take some term C here. Let this be C, this be C, this be C, and this be C. Correct. So here we have seen that C became 2C, but the rate became 4 times. That means C became 2C, that means it has to be in the square form. That means X has to be 2, because NO we have made it from CBC C squared to 2C square, if you see. That is nothing but 4C square, right? So that means 4 times. And that's what is happening, right? It becomes 4 times. That means X has to be 2. Let's repeat the same experiment, 3rd time. Here, don't change the amount of NO, let this be C only, but O2, let this be 2C. Now let's suppose the value came out to be 0.04 moles per liter per second. We'll take some numericals on this to understand, just telling you the concepts. Let's assume this is what happens. Now if you compare 1 and 3, the concentration of NO is same, but concentration of oxygen has become double, and the rate also became double. correct? That means it is to the power 1. See, c becomes 2c, or c square becomes 2c square, or c cube becomes 2c cube, right? Only three like this. X, I mean the possibilities are like this for the value of x. Now in this case 2 to 8, 4 times jump. So this is 2 times jump, this is 4 times jump, this is 8 times jump. Since there was a 4 times jump, that means I am talking about this scenario. That means the power is 2. The power was 2. In this second case, from 2 to 4, 0.02 to 0.04, 2 times jump. This is also 2 times jump, right? That means 2 times jump. That means I am talking about the power 1. That means y plus 1. So with this equation I can say that the rate is nothing but K into concentration of NO to the power 2, O2 to the power, and that is what we can conclude using this experiment. Please note, these are all experimental values. Rate law, all the values are experimental values. Just by looking at the equation, you can't say what is the value of x and y. This is how typically we find the rate law. For a given equation, we generally do this experiment and we find the value of x and y. Let's take some examples, or let's understand why do we need rate law equation. See, as I told that the impact can be different for different molecules. For example, again, the target is to break this tower. Break the tower, that is the target. Now, this yellow taxi may need 10 hits to break this. This jeep may need 5 hits. And this truck may need only 1 hit. So if you see, the impact of the truck is more, impact of the jeep is less, sedan is all the more less. So in this case, if you add concentration of, or if you add one more truck here, then the rate will increase like anything. But if you add, let's suppose you already have one truck, one sedan, one jeep, and the target is to break the tower, and they are breaking it, and they're taking some seconds or some minutes to break the tower. The moment you add one more truck, the speed will be very much increased. But if you add one more sedan, the speed will not be increased that much. Or if you add one jeep, the speed will be increased moderately. So if you see, there are 3 different reactants, right? But again, some reactant has more contribution, some has less contribution. Correct? More contribution and some has less contribution. So if you increase the concentration of something which has more contribution, the reaction rate will increase all the more. Thus, everything is not having equal contribution. So if you see in this case, just by experiment they found that for this the rate was concentration of CaCl3 to the power 1 and concentration of chlorine to the power half. That means chlorine is having less contribution for this reaction. Right? Typically in our life also, if you see, so if you want to increase the rate of reaction using rate law, we know that CaCl3 has more scope. So we'll increase the concentration of CaCl3 more than increasing the concentration of chlorine. Correct? So in this case also, we know truck is causing breaking this tower easily. So if I have to add one vehicle, I have a choice between truck, sedan and jeep. Obviously I'll go for truck because I know that the moment I add truck, the rate of reaction will increase. Right? The time it takes to break the tower will be less. Same thing here, if you know the rate law properly, if you want to moderate the reaction, you want to increase the rate of reaction, you know that this is the guy I am supposed to increase. If you want to decrease the rate of reaction, you know that this is the guy which I am to decrease the concentration to control the reaction. So to control the rate of reaction, it is very important to know the rate law for the reaction. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.